Hello students, so welcome to the IMS Gate Academy. So welcome to this Gate Score Booster sessions. In IMS, all the branches including computer science, even other branches also. Every year we start this Gate Score Booster session. That's end part of the preparation, like in the mostly November and December now. As part of this series, I would like to start from computer science, the subject which I have taken, computer organization architecture. Okay. So this is a crucial time period in which this period, like we have to focus on the revising the subjects. Correct. And we have to practice the questions like even PYQs or mock test, chapter level, subject level test. We have to do this in time. So thank you so much for confirming this the audio or video part. Okay. As I told you, like this Gate Score Booster session on this COA, I'll be conducting the 2 sessions. So one is planned today and other is 30th November tomorrow, same time. Okay. So in this session, what I will be discussing, I'll discuss some most important questions through which we'll revise the topics. We'll try to cover the most important topic from this computer organization architecture. So now repeated topics what are the more frequently asked areas from this subject we'll take, and in which some questions we'll discuss. So obviously we're revising the subject by practicing the questions here now. So definitely this session going to be help you a lot. Not only the COA, in the future other subjects also I'm going to plan, like operating system, computer networks, even compiler design also. So most of them might be aware of it, like not only in the CSE, even other branches parallelly already started the Gate Score Booster session. Try to utilize these sessions. Definitely these sessions are going to be help you a lot. Okay. So let's begin the session. Okay. So in this one, what I will discuss, as I told you, the 2 sessions I planned it. The first, so the 2 topics and the 2 chapters I'll be covering in these sessions. Okay. One is the first one is introduction to COA, the followed by memory organization. Followed by memory organization, in which memory hierarchy, followed by we also see this main memory, questions related to main memory, and followed by cache memory. Cache memory now. So these 2 topics I'll be covering in this session now. Another 2 topics like instruction set architecture, addressing mode and instruction pipelining, and the DMA controller secondary memory. So that I'll be covering into another session now. That is planned on 30th November, that is tomorrow. Okay. Coming into this one, introduction. Here mainly you understand now number representation now. So number representation. Actually this number representation is part of the digital logic design, right? But I'll not covering the fixed point number representation. The main number representation will be focused on floating point number representation. Floating point number representation. Floating point number representation now. Number representation now. Under this also major focus on IEEE 754 standard. IEEE 754 standard. There is a major focus on this part only now. And this topic also most important, we can expect the 2-mark question from this area. 2-mark question. 2-mark question can be expected now. So there was a question in 2025, even 2024 also there was a question like this. More frequently seen from this area. So from the past previous years you have observed it. So more frequently observed, there was a question from this area now. Very easy topic also, like you might have studied. So this Gate Score Booster session helping you, those already studied the COA subject now. If somebody not studied, just to look at the problem solving, like look at the problems, how you are solving the problem, that is also going to help you. But it is more helping for them who already studied subject, they are under revision mode. Now this help you to tackle some different areas. Okay, different observation we can do on this important topics. So good evening. So very good evening. Look at this first. So I'll take one question from this floating point number representation. Just I have taken very simple question you can say now. The modified exponent of IEEE 754 single precision floating point 32-bit number is given like this now. E is dash. He asked modified exponent field of IEEE 754 single precision. He asking now. Some number is given. So that number we have to represent in a IEEE 754 single precision format. So in which what is the modified exponent field is there now. So basically right, any floating point real number we represent like m into r power of e form. M can be plus or minus, it is a signed number. What is this m? It is a mantissa. It is a mantissa. So what is this? This is exponent. This is an exponent, right? It is exponent. So what is this? Base of the system, radix we can say. So radix are base of the system, we can tell, base of the system now. If I take binary, so my representation will be plus or minus m into 2 power of e like this. So most of the cases mantissa is a fraction. So most of the cases mantissa is a fraction. Therefore plus or minus dot m, it is a base, you can do base 2 power of e, you can say. This is a representation like this. Any floating point number I have to represent this format. Therefore, so memory access time for this mantissa exponent is less now. But this when it comes to IEEE 754 format, this representation like slightly changed it. This representation, if you see it, this one I'm talking here. So value expression also we can tell, right, this one now. So minus 1 whole power of s, because this sign bit is there. So now point, so this 1 point m base 2 into 2 power of small e minus bias. Small e bias is there now. So 1 point m we called implicit normalization also we can say. So implicit normalization we can say, right? So now this is this e minus bias, sorry, this must be some capital E I'm taking now. Capital E minus 2 power of capital E minus bias form, you have to store it now. And also right, the bias is in case of IEEE 754 format also fixed 127 fixed it. Therefore now value expression will be minus 1 whole power of s 1 point m base 2 into 2 power of e minus 127 is a value expression for implicit normalization under IEEE 754 format. The basics which right. So let's understand. Let's take this point. Sorry. Just a minute. Just remove this part. Now look this. Okay. So this number minus 1, it is the given number is minus 1 1.1100 110010. Okay. So 000, last bit is 1 into 2 power of minus 107 is given now. This is a number we need to represent now. So by looking at this number, what we can understand, sign bit is what? 1 now. It is a format 1 point m format is there, right? So 1 point m format is there now. So I can get the mantissa. Mantissa is what? 1100, 1 all zeros followed by 1 is there now. Into, so now this one is a mantissa now. Exponent, capital E. So capital E nothing but plus small e plus bias. Small e plus bias. So this only we called unsigned. So unsigned biased exponent we say. So biased exponent. So this is a true exponent, true or original exponent also we can say. True exponent or original exponent we can say. It is come from user. So now your bias is fixed. What is the bias here? 127 is fixed now, isn't it? I hope this is clear, everyone. Those who are watching, just confirm me. So those who are watching, confirm me. Is this correct? Yes. So exponent, like, because we stored bias form only, right? We stored bias form only, correct? Huh? So E plus bias form. What is the E value? Capital E. This is capital E equal to small e. What is small e? Minus 107 plus bias is 127, right? The capital E is what? 20 only, right? 20 now. S value is what? 1. So now mantis are already given 1 1 0 0 0 0, right? So 0 1. So 0 0 0 0, like, so this one now. So what is the mantissa size? 23 bits, right? So mantissa size is 23 bits. This is 1 bit long. Now this I can express 20 in binary, right? This is 8 bit is fixed, right? Now based on the options, if the option is given like, no, if the option is given binary, so 20 I have to express in binary now. Okay. If the mantis also given, I can write, select it. Now my sign bit is what? 1. So now just asking as exponent field. So what is the modified exponent field from this representation? My exponent field is 20. So 20 will come. Now 20 outright in binary. 16 plus 4, 16. 8, 4, 2, 0. Isn't it now? This is 20 now. So like 1, 2, 3, 4, 5, 6, 7, 8 bit. This is your answer now. In a binary format, one of the option is there now. This is my exponent now. So mantissa field is there. My sign bit field is there now. So means what I'm trying to say it here. So IEEE based questions, they can give some decimal number. They ask us to represent into what IEEE format. We have to get the sign bit position, sign bit value, mantissa exponent. This is a register, 32-bit register storage. Otherwise, 32-bit register is given. They can ask what is the decimal value. Many times, if you see the previous year questions, now 2 floating point number, they have taken representation. The addition of this 2 value, subtraction, multiplication, division, this type of questions also framed it. The first of all, I should know the format of the IEEE format, the like 32-bit format is there. So you also know this one, right? So if I say it, the register storage under this 32-bit register is what? Sign bit 1 bit will go, followed by mantissa. Mantissa 23 bits will be there. And sorry, so the second field is exponent. Second field is exponent, is a k bits will be there, and mantissa. Under this one, 23 bits are fixed for this 8 bits are fixed, this 1 bit is fixed now. This is 24 load total. So my register size is going to be 32-bit register now. So 32-bit register has three format, 3 fields is there: sign bit, exponent field, and mantissa. Mantissa 23 bits, 8 bit and 1 bit will be there now. So this representation, the ranges which then easily any number can be represented under this format. I hope this is clear now, everyone. So now coming into the point, as we IMS, like we have started all India mock test series, which is like the equal standard to the gate level. Now total 12 test series for computer science and 6 test series for data science. Okay, under preparation, some of them already live in this IMS 3.0, like as this portal, this is every year we new questions, the relevant to the current gate exam, we have prepared it, and some are under preparation only. So example, as the dates also clearly mentioned, what are the days the test became live. So suppose you take it, so 27th November, all India mock test, 8 is on live on 27th November. Next is the 10th December, like this, So last test is on the 28th January 2026. Okay. Total 12 test series are there with full length mock test. So I can recommend you, all of you, just you can log into this portal. Like those who are interested, you can purchase this, all in the mock test series for the various branches. So as part of this one, as IMS offering apart from this offline classes, we have online classes also. in which majorly we will be covering for almost more than 800 teaching hours. Okay, along with, so like no, you'll be getting the books like for theoretical books which relevant to the class, as followed by practice questions we call the exercise book questions. It has more than 4,000 questions. The main important property is that last 33, but there are 34 years of the previous year questions with the detailed and video solutions also available. That book also given to you. And the unique pitch of this IMS is a mentorship sessions now. So like no personalized guidance, like no, the student to student, the preparation changes like according to the student, because somebody somebody in final year, somebody in second year, somebody passed or somebody working professional. So each category require different types of preparation. So according to them, you can sit with a mentor and you can discuss. Such kind of sessions will be giving you more than 12. And when it comes to test, topic level, subject level, full length, multi-subject level, the test also having almost 130 test series available. Okay, so we have a zero fee program. You can log into this IMS 3.0 and just to go to the zero fee program. Is nothing to be paid. Just go and see this, the free content. You can register for this. So then eventually you can know those who are interested for this online program also can enroll it. Okay, chalo, we'll coming to the another questions. So before going to these questions, as I told you, as introductory part of this computer organization architect, what student has to focus it. You must aware of this fixed point number representation as well as floating point number representations. The format you should know. Therefore, any basic questions comes, you are able to answer it now. Some observations you can see it. So unsigned integer range is 0 to 2 power n minus 1. I hope this is clear. This line is clear. Just confirming. Any unsigned number with a where n is a number of bits, binary representation I am taking. Unsigned fraction range 0 to 1 minus 2 power minus n. This is for binary fractions. Sign magnitude range is with n bit number. If you take this is a range sign magnitude, 1's complement, 2's complement. No, you might have prepared as a short notes. Just recall. These are the important now. As I told you, floating point number and represent value expression is what minus 1 whole power of s into 1 point m base to 2 power e minus this explicit normalization we call. Implicit is 1 point m. Just now I written it. Implicit 2 power e minus 127. Bias is fixed. We called implicit normalization. Basically, this implicit normalization we using what? IEEE 754 format. Under IEEE 754 format, we use this value expression. So just a little more details I want to discuss on this IEEE format. If you take IEEE format, you might have know, if you take 32-bit pattern, so this 32-bit pattern, let me take 3 different cases to get the clarity. Okay, 3 cases I'll consider, sorry, not 3 cases, 5 cases I'll take it. Let's take this 32-bit number divided, sign bit is 1, correct? And exponent capital E is having 8-bit, right? Now, so mantissa for this 23 bits are there given to, right? What this value denotes, will observe it. Okay. If you know this 5 cases, any type of question comes related to this one, you are able to answer it. So case number 1, okay. So before studying of IEEE 754 format, because you understand in 1980s, probably if I am not wrong, IEEE 754 standard came into picture. That means all the computer architecture must use this IEEE format standard for representing real numbers or floating point number. Because before this 1985, before this IEEE format, every architecture they used to have their own mechanism to represent number. Such cases, mantissa field, exponent fields are used to vary. If you observe the IBM architectures of 16-bit, 32-bit, other architecture used to have differently. Before this IEEE 754 standard, when IEEE institution has given a patent for representing all floating point number in this format only. So now onwards, that time onwards, every architecture who design computer system architecture has to follow this format only now. And there are many, like IEEE given, there are many standards, 32-bit, 64-bit, even beyond the 64-bit, there is a 128-bit extended format also there. Single precision we call double precision. Extended precision also we can tell, that is a 128 bit. Some of the architectures will support that also, right? If I look at the 32 bit architecture format here, the case number 1, sign bit can be 0 or 1, as I know, sign bit are 0 or 1 now. If this E is 0, E is 0 means all 8 bits are 0. Also I am taking, if this M is 0, all 23 bits are 0. What is representing? Plus or minus 0 represents. Now normal fundamental IEEE representation, if you see 0, there was no provision for representing 0. So IEEE is given a provision for representation of 0. So similarly, case number 2, this sign bit can be 0 or 1. If this E is full means what? All 8 bits are 1. This number will give 255. The case I am taking, M is still 0 now. Is still 0. So this will represent, plus or minus infinite. So larger than largest number, like this number also representable. There is a pattern for representing infinite. Case number 3 is a normal number, you understand. So sign bit can be 0 or 1. If E is between 1 to 254, please understand now. 1 to 254, because 0 is reserved, 255 reserved. So E is possible between 1 to 254. If this M, like M can be any combination. So this represents implicit normalization. So implicit normalization number. So before equation we see implicit normalization can be there now. Case number 4. Sign bit can be 0 or 1. Now. So now this I am taking the scenario. If so, this D normal number, if exponent is 0. Now if M is not equal to 0, fraction. This also fractional form or D normal number also you can say. So D normal number also you can say. This we are able to represent, smaller than smallest number also can be representable here. Case number 5. Sign bit can be 0 or 1. If this E is full, 255. If this M not equal to 0, any pattern is there. This number not able to, not a number we say. Not a number means some patterns cannot represent. Example, square root of -1 not representable, like this, square root of -2 like this. So like 0 by 0 like this. Some are things are not able to represent, that comes under case number 5 now. Okay. All normal numbers between E 1 to 254, a D normal number is what? E must be 0, fractional form. Okay. So now when it comes to this one, just a minute, implicit normalization expression we know, right? So implicit normalization expression, that value expression just now written, -1 whole power of S 1.m base 2 into 2 power of E minus bias, right? So now D normal number. So D normal number value expression is -1 whole power of S. Now this is a fractional. So let me write 0.m1 base 2 into 2 power of minimum E is possible is what? 1. So this value when it is 1, so minimum E possible is what? 1. When I take 1, so 2 power of -126 now. The smallest number, 2 power of -126, right? 2 power of -126. The smallest number you can able to represent it, right? This is the smallest number. So there was a question, GATE 2025, if I am not wrong, they asked like, what is the smallest number can be representable in IEEE 754 single precision format given? That is a number. But they ask in terms of fields, sign bit field, mantissa field, exponent field. They give an option. We can able to select it. If you know that what is the largest number, smallest number, what is normal number, D normal number, yes, we can able to do it, right? Yes. So I hope you understand this one. So just observe these 5 cases through which any type of question comes in this area, you are able to solve it. Yes. Okay. So we'll move for another area. We'll move for another area. Another area. These points are important. What these are points are here now. Number arithmetic. Sometimes questions also we can expect from a number arithmetic operations, like in terms of addition, in terms of subtraction. So in terms of multiplication, multiplication can be integer, like unsigned multiplication, signed multiplication also comes now. Some observation from this area help you to solve the problems. Let's take example. If ones or twos complement notations are used, then overflow is detected by one of the following. What is this line I am saying you? So normal unsigned addition multiplication is normal only, like as a division format only you can use it. The point we need to understand for integer, like signed integers only now. When two signed integers you are adding, when two signed integers you are multiplying, so that cases a special things need to be observed. Suppose you take the arithmetic operation as addition now. Signed number I am using now. Signed number addition now. Okay. As we know, whenever signed numbers are there are three notations we have for representation, right? One is ones complement, sorry, sign magnitude, ones complement, twos complement. Am I right, all of you? Those who are watching, just confirming. Any signed integer can be represented in three format. Sign magnitude, ones complement, twos complement, right? Okay. If you are using this one of them, ones and twos complement notation for representing the signed integer, when you are adding, how to detect the overflow? What is the meaning of overflow? If two number you are adding, the results you are not able to fit in the same range, that becomes overflow now. So one thing I can understand, when two different sign numbers you are adding, there is no question of overflow, isn't it now? Correct? When two different sign numbers you are adding, and two different sign numbers you are adding, so there is no overflow. When same sign numbers added, when same signs are subtracted, isn't it? There is a problem of overflow can happen, may happen, you understand now. If that is happen, how to detect the overflow? The two rules are there, which are easy now. So one is this rule number 1 and rule number 2, you can use it problem solving now. If ones or twos complement notations are used, then overflow is detected by one of the following condition now. Number of, numbers are of the same sign numbers when you add, result came opposite sign. During this condition, the result is an overflow. Simple. When two sign numbers are, when you are adding, two signs are there, same sign numbers are there, result is came opposite. Definitely there is a overflow. So other way also, carry in bit into sign position, carry out of the sign position is not same. Then also result in overflow. There are two ways are there to detecting overflow under signed addition of numbers now. Similarly, if the sign magnitude numbers are, if the sign numbers are denoted sign magnitude notation, then presence of carry out at this sign position denote overflow. So carry out bit is 1, if it is present at sign bit position, that becomes overflow. So this way you can test overflow condition. Let me take one example to understand, to get a clarity on this one now. If I take example, minus 80, minus 70 number is there now. Two sign numbers I am adding. So two sign numbers I am adding. Let I am taking 8-bit number. Let 8-bit binary number. Let 8-bit binary number is to represent the. So represent this numbers, understand. 8-bit number I am giving you. Tell me, under 8-bit number, what is the range in case of twos complement? If I use twos complement range, 2 power of what you can say, sorry, 2's complement, right, minus 2 power of n2 plus 2 power of n minus 1, isn't it? Minus 1, right? Yes, sir, this is the range. So that nothing but 2 power of 8 minus 1, 2 plus 2 power of 8 minus 1, minus 128, 2 plus 127. This is the range, isn't it? This is the range now. Okay, getting my point now. So now when I add this number minus 150, correct? 150 can I able to place in this range? Suppose 80 can I put it in this range? Yes, possible. 70 can I place in this range? Possible. When I add these two sign numbers, the result will go to 150. 150 you cannot place in this range. Definitely this must be overflow. But as a decimal we represented, we understand there is overflow. So, but how to get this overflow? How to test it? That's what two rules are there now. Suppose if I express this minus 80 in 2's complement. Tell me minus 80 in 2's complement, how to write somebody? Tell me. Minus 8, this type of questions compulsory comes. There was a question 2025 gate, some number minus, how much given? Minus 6 given now. Minus 6 represent in 2's complement for 8-bit and 16-bit number he asked it. 2 mark question frame. If I am not wrong, 2 or 1 mark. Minus 6 we have to represent 2 in 2's complement notation. Minus 6 we have to represent 2's complement. So tell me how to represent minus 18 2's complement. 2's complement in minus representation of minus 80. One way first get the sign magnitude. One way is what? Get the sign magnitude, then convert it into 1's complement, add 1, that becomes 2's complement. Otherwise, directly I can write it in position wise. So bit range, bit positions, right? First bit, like right to left, if I go first bit, LSB bit position is 2 power of 0, 1. Next 2 power of 1, 2, 4, 8, 16, 32, 64, 128 will go right. So always look at this number, next range you go it. Next bit weight you can say like now. I hope you are understanding, Bit weights are like 1, 2, 4, 8, 16, 32, 64, 128, like this are there, right? So now if I plotted this one, this 128 bit position I am taking, 128 bit position. If I plotted this one, if I take this one, this weight will come. Under 2's complement representation, if you know, sign bit as the negative weight. So minus 128 will come. How much I should subtract? Therefore, minus 80 has to, I have to represent minus 80 only, right? How much I have to subtract to get 80? 40, 48. So means this 32 plus 4, 40. Sorry, I can make it this one, right? 48 only, right? So 48, 0, 0, 0, 0, right? 0. This is a minus, minus 80 representation. Minus 70, how to write same? So 128 bit if I take it, how much I have to subtract? 30 plus 28, 58 I have to subtract it. So 58 means this must be 0. This I have to take it, right? This is 48 plus 8 is 56. This one I have to take it, right? And 2's complement now. So I'm adding these two numbers, right? We're adding these two numbers. Check it, this is correct. 70 represented 2's complement is correct. All of you check it. Yes, my everyone. Yes, yes. 70 represent 2's complement. 70 represent 2's complement. Is this number is correct? Is this number is correct? So 128, negative 128 we have. So 32 plus 40, 56. 56 plus 2, done. So this I am adding 0 plus 0, 0. 0 plus 1, 1. 0 plus 0, 0. 1. 1 plus 1, 0. 1 carry. 1 plus 1 plus 3. 1 sum, 1 carry. 0 plus 0 plus 1, 1. Right. Now see, 1 plus 1, 0, right? 0, 1 carry. So I hope you are aware of it. When you are performing 2's complement arithmetic operation, if you get a carry, you can ignore this one now. This is your result. So now see, what is the sign of this number? Negative. What is sign of the number? Means how to know sign of a number? If leftmost bit is 1, negative. If leftmost bit is 0, positive. Sign of a number is negative. Sign of a number is negative. Sign of a number is positive. Rule number 1 I told you. Numbers are of the same sign. The result is opposite sign. During this condition, this is indication of overflow only now. So both are same sign added, result is opposite. So indication of overflow. This way we can detect it. Just I want to know the mechanism to how to detect that there is a overflow when I am manipulating signed integers, maybe addition, subtraction, but it's not the case multiplication, you understand. Multiplication will dealt differently. Yes, everyone. I hope this point is clear. So similarly, we can also check, use this carry in bit into sign position and carry out sign bit position is not same, then also result overflow. So you can see now. So when I 0 plus 1, okay, sum is 1, carry out is 0. Correct? For this carry, so for this position, carry in is 0. From this carry out is what? 1. Carry out, carry in are not same, then is also overflow. This way I can test it. So this information is sufficient from this area. So we'll move for another area, memory organization. As I told you, in the memory organization, we can focus first on memory hierarchy based questions, followed by, let's see, the cache memory. Very important topic for this one now, followed by main memory now. Main memory. Okay. So cache memory much important. Confirm we can expect the 2-mark question here now. Here also we can expect the 2-mark question, sometime 1 mark. And main memory also. From here only we can expect 3 marks to 5 marks is possible. 3 to 5 marks possible from this area. So when it comes to cache memory, you might have studied main address mapping schemes are much important here. Address mapping methods. Address mapping methods. Did you study all of you methods? So one is, name it as a direct address mapping. Direct address mapping. The second one is what? Full associative mapping. Full associative mapping. The third one is a set associative mapping. Set associative address mapping now. These are 3 important. So 3 important mapping methods are there. What is the purpose of mappings? Purpose of mapping, converting the cache address into what? Main memory address into cache address. Correct? So if I take this one, okay. So I'm saying that this is a memory hierarchy. The memory hierarchy is there now. Okay, you take cache memory. Here is the main memory, right? Here is the main memory, and this is what secondary memory is there now. So main memory to we have to map to, like secondary memory to main memory mapping taken care by operating system. Translation, address translation from secondary memory to main memory taken care by operating system. Generally we call virtual address space, we can say. This we call physical address space, we'll say. Translation from here to taken care by OS now. From main memory to cache memory, main memory address is physical address. This address is what? Cache address space. So main memory address space to cache address space you have to translate. This is taken care by cache hardware, cache controller we can say. Hardware only, simply we can say hardware. Hardware only will translate this one now. So by using 3 mechanisms are there. Direct address mapping, full associative, set associative. If I am not wrong. Clear all of you? So now this address is there, this address. Address which you given to memory we call physical address we call, right? Physical address only we call now. Correct? This physical address we have to translate into cache address now. Physical address translated into cache address now. So that is what I'm trying to say is there is a CPU. There is a CPU like this, some process PI is running now. Here is a main memory, please understand. Here is a main memory now. Main memory, okay. For this main memory, what I told you, physical address will be there, right? Okay. Main memory, physical address will be there, right? Main memory, physical address will be there. Correct? Main memory, physical address is there now. So generally processor, CPU generate this address. The address we call logical address. So this logical address is translated into physical address to search something in main memory. So with the help of operating system, will take the responsibility this one now. Operating system take the responsibility to translate from logical address to physical address now. Physical address to means nothing but you have to able to search something in main memory now. Correct now. But for the optimization to reduce the average memory access time, we are keeping cache memory. We are keeping cache memory, right? What is the purpose of cache memory? Cache memory contains frequently repeated data and instructions, right? Simply it is maintains locality of reference, you understand now. Due to this locality of references, average memory access time drastically reduces here now. This because of cache, I can have levels also, level 1, level 2, level 3 also I can add it. Okay. Now understand now. So processor generates address always to memory only now. It is generally going to access the memory into main memory only now. But to reduce average memory access time, we added cache. Therefore, this physical address you to take and search here cache first. If this is present in a cache memory, you take a data from cache given to the processor. If cache miss occur, we should go to main memory, bring some data, place into cache memory given to the processor now. So this translation of memory, like now, when there is a missing cache memory, we have to go to memory, bring and place and give into processor, right? So this mapping is happening now. Main memory to cache memory mapping happens. This one, no? Main memory to cache memory mapping happens now. Okay. So there are 3 mapping methods as I told, right? One is direct address mapping. Under a direct address mapping, so this address, the physical address going to memory, correct or not? We have to take this physical address, you know, this one. You search this using physical address, your search in cache memory. If I follow direct address mapping, the physical address is divided into 3 parts. I hope you know. One is a tag bits, other is a block offset. So block number, word offset, word number will be there. If I use the second technique is full associative address mapping, if I use it. So under this cases, physical address is divided into tag plus only word offset will be there now. If I use set association, so set associative address mapping technique, if I use it, this physical address, so physical address divided into 3 parts. One is a tag, other is a set offset and word offset will be there now. Okay. So you might have studied all mechanism clearly, individually, one by one. Their advantages, limitations, all the things you might have studied related to this one. I don't want to go inside because it takes a lot of time. Okay. So I am taking here relevant to this one some questions. Let's solve it and let's observe some important point from this here. Yes. I hope everyone it is clear now. Okay. What is the idea? The processor will generate the address, generally we search in main memory, but due to there is a cache memory is present, therefore first you search in a cache memory. If it is present, take it. If it is not present, bring from main memory and place in cache given to the processor now. So now reading something like no placing from between cache main memory, this one address translation will happen by using various methods like direct and full associative, set associative. This part we will see. Before this one now, so there are various memories we have, right? Like as I told, cache, main memory and secondary memory now. So we have to arrange them. Therefore, no average access time reduces. So memory hierarchy we call basically. Arrangement of this memories is a memory hierarchy. The objective of memory hierarchy is to reduce the average memory access time. So related to this one, some questions, let's solve it. So there is a question like a system uses two-level cache. For every 1000 memory access generated by the CPU, 920 it's in L1 cache and 64 it's in L2 cache. Access time of L1, L2 and main memory is given something like this respectively. Calculate the sum of the local miss rate of the L2 and global miss rate of the L2 is dash up to 3 decimal places he is asking now. So I want to this question intuition to take it to know what do we understand, what is the local miss rate and global miss rate here. Local miss rate and global miss rate. Let's take the scenario. This is CPU, right? CPU. And taking the scenario is L1 memory followed by L2 cache memory followed by main memory is there. this is a connected main memory, cache of level 2 cache memory, you can say level 1 cache memory. You understand now? CPU generated 1000 references, generated 1000 references. So all 1000 reference means for some address generated, that address you have to search in cache memory now. That address we have to search in cache memory. So now this one you understand now. Okay, L1. So what is L1 here said? For every 1000 memory references generated by CPU, 920 it in L1 now. It means, what is the meaning of it? It means if the referred word is present at referred level, that is the become it. If the referred word is not present at referred level, that becomes miss now. So I'm saying that it ratio. Okay, it ratio, right? It ratio is 920 its out of 1000. So, sorry, 920, right? 920, right? 920 out of 1000 now. So this is a it ratio. Simply you can say 92% I can tell, isn't it? Yes, sir. 92% it ratio is there. So now remaining misses will go to where? Here only, correct or not? Suppose how many will go? 920, 80 will go to this one, right? 80 references will go now. 80 will go to this one now, L2. So out of 80, what is said here? Cache 64, it's in L2 cache, 64. So out of 80, 64 it. Now I can write it ratio of, so let me use L2. It ratio of L2 64 out of 80. Okay, now. So remaining will go to where? Here only, right? Remaining will go to main memory only. How many now? 64 means what? 6 plus 10. 16 will go here now. 16 will go here now. 16 references will go. Okay. So what is the question here? Calculate the sum of the local miss rate of L2 and global miss rate of L2. Okay. For L1, there is no local global. Everything is like directly global only we can tell. Like, because every reference generated by CPU will go to level 1 confirm. Every reference will go to level 1 only now. That's simply the global miss rate only, right? M1 is the miss rate of L1. If I take 8% is a miss rate only, because here is 80 by 1000 you can say now. 8% miss rate is there now. Who is the miss rate? L1. Now 8% only, this 9 to 80 only will go to here, right? 80 only will go to here now. Out of 80, how many are it? 64 are it now. What is the miss rate of L2? Miss rate of L2. Let me use local miss rate. First I am taking local. Local means how many references came from L1 to L2. What references came from L1 to L1? When there is a miss in L1, then we are go to what? L2. That is the local miss, you can say. How many came here? 64. Sorry, 80 came now. Out of 80, how many are miss? So 16 are miss now. 16 by 80 becomes a local miss rate. Similarly, global miss rate. So global miss rate of M2 will be, I am saying that the 16 miss out of 1000. Okay, whatever miss happened in L2, you have to just compare to total number of references generated by CPU now. Total number of references generated by CPU, you have to see it now. Therefore, local miss rate of M2 equal to, what is the value? 16 by 80. So 16 by 80. So global miss rate of L2 will be 16 out of 1000. This you have to understand now. So this value you have to calculate it. Some of you tell me 16 by 80. This anyway 0.2 only, right? This 0.016 only, no? The sum of this one. sum of L of M2 plus G of M2 equal to, so 0.2 plus 0.016, 0.1216, this one, 3 decimal places now. Yes, I hope this is clear now. So I'm just bit interested here. What is average access time of 3-level system if I ask you? 3-level system now. This is a 3-level, right? L1, L2 main memory is there now, right? Their access time is also given now, correct or not? 10, 40, 500 nanosecond is given now. If I ask you, what is this average access time 3-level memory system? The direct expression, 2025 GATE also there was a question like this. So I can make it, T1 is compulsory plus a miss rate. When miss occur in L1, so penalty required, that is T2 level 2. If both the case miss occur, this becomes what? T3, I can rate it. What is the T1 value? So T1 is, T1 is 10, 40, 500, right? So 10 nanoseconds. M1 miss rate. Okay. So always miss rate of M1 miss rate. What is the miss rate of M1? So M1 miss rate is what? 8%. So 8% into M2 access time is what? What is M2 access time? 40, 500, right? 40 nanoseconds plus M1 8%. M2 is what? So M2 is this, you have to take it, so 0.2%. Am I right or not? This value only you have to take, because 20% will come, right? 20% is the miss rate into T3 is of 500. This you have to simplify. So 10 nanoseconds, 8%, 0.08 into 40 nanoseconds plus 0.08 into 0.2 into 500 nanoseconds. So this you have to simplify it. Whatever answer you get, that is only average access time of 3-level system. I hope this is clear, everyone. Let's move to another question. So just look at this question, try to attempt it. Yes, all of you. Try to attempt this question. What is the question says here? To improve the cache performance, system designed with a multi-level cache. System contains 2-level cache design and CPU generate 500 memory references in the program. If 100 misses operations occurred in level 1 with the heat time of level 1 cache is 40 nanosecond. 50 miss operations occurred in level 2 with heat time of level 2 is 100 nanosecond. Miss penalty of L2 cache is 300 nanoseconds. So what is average memory access time and what is the throughput of the memory system you are asking now? What is average access time of 3-level system is asking, followed by throughput of the system also asking. Throughput of the system. Yes. Try it out, try it out. Multi-level cache system, 2-level cache design is given. Okay, CPU generate the 500 references. Here is a CPU. Okay. So it generate the 500 references generated. It goes to level 1 cache. Okay. Level 1 cache. And there is a level 2 cache also there, right? L2 cache is given now. And miss penalty goes to main memory now. This is a main memory. Then always we get a doubt here, dear students now. Sir, this two-level memory caches and main memory is connected in the architecture. Are there level by level or parallel connection? That's a doubt always will get it. So, but this is a level by level. How I know this level by level? No, miss penalty. Use the word miss penalty of level 2 to cache is 300 nanosecond. If something is miss occur from level 2, it is connected. Go to what main memory only now. So miss penalty from L1 is not connected to what main memory, right? So there is also case, L1, L2 may be generally L1, L2 may be level by level and main memory, but L1, L2 will not be in the same level. We have to give it, one by one. The only question is that all three components are parallelly connected and level by level connected. So by using some words, if they use such words, miss penalty, suppose if there is a miss, you bring something from here. This kind of words is given. We can understand level by level connection only given to you this. If 100 misses operations occurred, L1, okay, with the level 1 access time 40 nanosecond, or let me take level 1 access 40 nanoseconds given now. So this access time is what 100 nanosecond is given now. Miss penalty is nothing but main memory access time is 500 nanosecond is given, if I am not wrong. Oh, sorry, 300. So it is given as 300 nanoseconds given, 300 nanoseconds given now. So I want to know this miss rate, M1 I am taking miss rate of L1. If 100 misses operation occurred in level 1, 100 out of 500, 100 out of 500 is a miss rate. Similarly, M2 miss rate I want to know, M2. For M2 whatever comes, for M2 it will come from M2, it will come from level 1 only, right? We should not take the global miss, we should take the local miss only, because for M2 it will come from L1. 100 misses, 100 miss happen now, 100 will come. So 100 will be the denominator now. So how many miss will be there, he said? So 50 misses operation occurred in level 2. So now 50 out of 100. Okay. M1, M2 we got it now. Okay. So now first question is what? T average access time. You might have studied various expressions, I mean the different format, but simple way I am telling how to take it. 3-level memory, 3-level system is given, how to get the average access time, very simple now. All the reference it in every level or not, first compulsory you have to search in L1, isn't it? Am I right or not? Try to understand. When I am taking this average, whether other levels it or miss, level 1 it or miss, every reference has to go to L1. So T1 access is compulsory required now. When there is a miss here, when there is a miss, I have to go to L2. That means what? That into miss penalty will come now. If both the case miss occur, will go to main memory. That's what M1, M2, then T3 will be there. If you know this expression, this gives the average access time of 3-level system. So what is the T1? 40 nanoseconds. M1 is what? 100 by 500 M1 miss rate. Into T2 access time is what? 100 nanoseconds. So M1 again 100 by 500, right? 500. Into what is M2? M2 is 50 by 100. 50 by 100. What is the T3? 300 nanosecond. 300 nanosecond. We have to simplify these values. You can this G cancel, and this zeros cancel. Okay, 1 0 1 0 cancel. 5 5 also cancel. The 0 0 also cancel. We'll get 30 nanoseconds here. Here how much it will come? 50, isn't it? 50 only? Not 50, 20, sorry, 20 only. So this is 20 will come now. This entirely 20 nanosecond. 40 plus 20, 60, 60 plus 30, 90 nanosecond will get it. So 90 nanosecond average access time. Check, all of you check, do check. Is it correct? The values are correct? Yes, 90 nanoseconds average access time. Now first question we got the answer. The second question is a throughput. Second question is what? Throughput. What is the throughput? Throughput is, it is also, we can say, bandwidth of this memory also. We can say, bandwidth of the memory also we can tell. Sometimes they use the word bandwidth. bandwidth. Or else you can say data transfer rate of the memory also we can tell now. Data transfer of the memory also we can say. Okay, number of words transfer per unit of time. It is simply 1 by average access time only. Just understand. You can use this expression now. So 1 by 90 nanoseconds. 1 by 90 nanoseconds. So 1 by 90 nanosecond. 1 nanosecond equal to 10 power minus 9 seconds, isn't it? So I can rewrite 1000 by 90 into 10 power 6, that is a word, right? Words per second I can use it. Use the words only. 500 references, okay, word only can take it. So 1000 by 90 into this we can write it. No? So this, if you simplify it, you can simplify. What is the value will come? So 11.12 I can write it. Mega words per second you can say. Or else you can make it approximately 11 megawatts per second also I can write it. So based on the options, based on the points given, you can select it. So I hope this data and these two questions related to this is clear now. Everyone. Yes. Let's try another question. Okay. Consider main memory of computer system consisting of 2M blocks, and cache has 2M blocks. Main memory, cache memory having same number of blocks is given now. If the two-way set associated mapping scheme is used, kth block of main memory to be placed where? Which set you have to place it? You might have studied 3 methods, right? One is direct address mapping. Second one, just now I told, full associative address mapping. And third one is a k-way set association. K-way set association. In this case, kth block of main memory you have to place in a cache. K modulo n we can say. This is a function we use it. Where n is the number of blocks in cache. Here is no function at all. You can place anywhere in the cache. In case of here, no kth, let me use P to avoid this confusion. P-way set association. So kth block of main memory should map to S. What is S? S is the number of sets. So number of sets. This is a function we use it. This line number, this set number you have to place it. This gives a set number. K modulo S to set number will give. Within set you can place it anywhere. So this is the functions we use it under PV set, set association under direct address mapping. Correct? Clear all of you? Now, cache memory consists, so number of blocks you can take. So number of blocks in cache memory. So number of blocks in cache memory, M, 2M. We need to find out number of sets. How to get the number of sets? Number of block divided by P-way set association. Used two-way set association. Two-way nothing but it should divide. You will get M. M sets we got. M sets we got it. Okay, what is the mapping function? So mapping function, what we use it here? Yes, tell me. Mapping function is kth block, K modulo set number, set. How many sets? M sets. K modulo M only. I'll use it. We write it K mod M. I can use it. This is only simple thing now. K mod M. Yes, option D is right. I hope this is clear. Let's move on to this. Consider P-way set associative cache with 8P blocks are there. Assume that main memory has 16P blocks. What is the tag size in this organization? They are asking simply tag bits only they are asking. Tag bits. Which way? P-way set associative. P-way set associative physical address, I hope you remember, is divided into 3 formats, right? One is a tag bits, set offset bit and followed by word offset bit, right? Am I right or not, all of you? This is a physical address divided now. So they're asking this value only, tag bit they're asking now. How to get set offset bits? So basically we should know number of cache blocks. If you know number of cache block, we can get the number of sets. If you get a number of sets, log to the what set, number of sets, you will get the set offset. Word offset depends on block size, log of block size, right? Set offset, well, how to obtain? Log of sets. Capital S we can take no number of sets, log of set. Now these two if you subtract from physical address, we'll get tag bits. I hope this is clear now. Yes or no? Now here cache memory given now. So let me given data take it. Okay, number of blocks. So number of blocks in cache memory. So number of blocks in cache memory given. P-way set associated cache with 8P blocks are there. 8P I'm writing now. 8P blocks are there now. So what is a way set association? P-way set association they used it. Okay. So number of blocks in main memory also given. Main memory is given, 16P is given now. 16. Assume that main memory has 16P blocks. What is the tag size in this one now? But lot of data indirectly given now. No, actually we don't know physical address here. We don't know block size also, we don't know. Because suppose if you know block size, number of blocks into block size will get a main memory size, I'll get it. If you know the main memory size, I can get the physical address. Therefore physical address I can divide into 3 formats, I can do it. But not given, physical address not given, block size also not given. Just we have number of blocks in cache memory, number of blocks in main memory, and set size is given now. That's it. But we should get the tag bits here now. Very interesting question and little tricky. Tricky is there in this question now. But we are able to answer it. Try it out. So those watching right now, you can try, and those who are going to watch later, you pause the video that moment and work out yourself and check the solution. Very interesting question this one now. One important property I would like to tell you. Related to this one now. So as we know physical address, let's take physical address. The physical address divided into 3 parts, right? One is a tag plus set offset under this P-way plus word offset is there, right? This is a format we have, right? This is a format. Yes or no? Okay. This word offset related to what? Block size. It is related to block size or not? Block size. I don't know block size, so I can ignore this value. Look at this one now. Set offset. Set offset related number of sets. How to get a number of sets? If you know number of blocks, so number of sets I can calculate. Let me calculate here. So number of sets if I want to know. So number of sets, capital S if I use it in cache memory. Number of blocks divided by set. Which way? P way means P have to do it. We got 8 sets we got. With this one set offset bits, can I find out or not? Set offset bit is a log of this value only, base 2. So 3 bits we got set offset. 3 bits we got set offset. So this set offset we got. We need to find out tag, correct or not? We need to find out tag. So what is the purpose of tag bits? Tell me. The purpose of tag bits, which block of main memory present in cache, isn't it? Tag bits will tell which block of main memory. If you clearly observe how to obtain tag bits also, tag bits generally we observe log of main memory block, suppose M is there, M by what you can say, how many blocks will present, right? M by N we can tell. Will it give m by n number of blocks? No, no. Let's take example I'm taking, 4 blocks are there. S base 2, yes, m by s will get it. M by s we can tell. M by n case of direct address mapping, main memory blocks will map to, so at a time, suppose if I take direct address mapping, tag bits will be, how to obtain m by n we can tell. Total, so where m is the number of blocks in main memory I'm taking now. If I take n number of blocks in cache memory, m by n if you divide it, will get it, tag bits will get it. In case of set associative, m by s, where s is the number of sets we can tell. Okay, means you understand, tag bits also related to it will come, no, and tag bits, so I'm saying, no, this thing, this way can drive, this can derive or drive, so derive number of blocks, so number of blocks in main memory I can tell, if you observe carefully. Okay, here I'm getting these two components, just I'm thinking. Okay, tag bits will get the, how many will map, set up, because the entire physical address will has to give main memory only, right? This entirely, so physical address, this entire physical address you take it, that will give the main memory size only. Am I right or not? Because it has to give it. So word offset is related to block size. Block size I'm not removing. So this entire thing has to give it number of blocks in main memory only now. So number of blocks in main memory has to give it this one. If you observe carefully, because here is a number of sets will come. Number of sets, if you know, each set how many blocks are there, that also I can get to know correct or not. Now tag bits how many will be mapped to here now. Together we'll able to divide. That means I can able right now tag bits plus set offset bits equal to, okay, so number of bits required to address the blocks in main memory. That's simply log of number of blocks. Let me take like this, base 2. What is the number of blocks in main memory? Number of blocks in main memory. Okay, let me give you one example to get a clarity over this one. Suppose main memory I'm taking like this for the clarity, So main memory has some, let's take 32 blocks are there, assumption now. Simply 1, 2, 3, 4 like this. 32 blocks, 0, 1, 2, 3, 4. So 31. So capital M I'm taking as 32 blocks are there. Let me take cache memory also. Cache memory has 8 block assumption now. 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7. Okay, capital N I'm taking as 8. It is a cache memory. It is a cache memory. Let me use two-way set association also. Two-way set association means how many sets? 1, 2, like set number 0, set number 1, set number 2, set number 3. So now S value is 4. S value is 4. N value is 8 here. Okay. N value is 8. Let's also take it block size is suppose 16 words are there. 16 words are there. Some physical address under this mapping, tag plus set offset plus word offset will take it now. Word offset required 4 bits required. Set offset required how many bits required? Set offset bits means number of sets. How many sets we get? 4. So 2 bits required now. Tag bits we have to get it now. Okay. Now here, how we can map them here? 32, like suppose I have to take anyone, you have to map to set number only, right? Set number only have to map it now. So so now M by S if I take 32 by 4 is 8, 3 bits required. Let's take this value is what, 9, correct. Tag bits we got 3 and 32 blocks and each block 16. What is the main memory size? Now main memory size is now 32 into 16 words are there. 2 power of 5 into 2 power of 4, 2 power of 512. 512 words are there. Physical addresses, let's take 9 bits. Correct. Physical address 9 bits are there. Physical address 9 bits. I can segregate 3 plus 2, 5, 5 plus 4, 9. Correct. Now listen, because I want to look at the formula is correct or not. If it is a direct address mapping, what happens here? Now that this 4 will not change. 32 by 8, if I take it, how many block offset will be there? Number of, so 8 means 3 bits will go. Tag means will go, suppose 8 is there. Block offset 8, block of number of blocks are 8 means 3 bits will go here. 3 plus 4, 7. 2 will come. How 2 will come now? 32 by 8 is 4. 2 bits will represent tag 1. That's correct. Now come to the point. What I'm trying to say, these two fields will able to find out the number of blocks in cache memory, main memory. These two fields helping me to find the number of blocks in cache main memory. I want to understand. How see? 3 plus 2. 3 plus 2 value, how much? 5. 2 power of 5 value 32. So there are 32 blocks are there. So now to find the number of blocks in main memory, I don't want this data. If block size not given, still I am able to get it. Number of blocks in main memory. Now come to my question. So number of blocks in main memory given 16p, right? So that's what I am able to relate, Physical address tag plus set offset, word offset is there. This one. In this component, these two able to derive the number of blocks in main memory. So tag bits plus set offset bits equal to log of main memory blocks only. Or else 2 power of this value will give the number of blocks. Now, so tag bits I am writing now here. So tag bits. So set offset bits we got 3 log m. How many blocks are there in main 16p? So 16p base 2. Okay, now. So we need to find out tag bits only, right? Tag bits. So tag bits equal to, I'll send this side, right? So this we can write now log 16p nothing but log 16 plus log p. So this will come, what you can say, so p plus 4 minus 3. So log p will be, log p. So log p base 2, 16 means so 4 minus 3. So therefore simply log p base 2 plus 1. So this is your answer now. Log p plus 1 base 2, right? Log p plus 1. So this is your answer now. So this is your answer, right? I'm able to get it now. So now what is observation from this question? If some data, full data, if it is not given also, still we are able to answer the question. That we have to learn from this one more. So this is a very important point. This mapping now. So my alone tag and set offset bit help to find the number of blocks in cache memory, main memory. Similarly, alone tag plus block offset in case of direct address mapping also able to derive the number of blocks in main memory. So we can ignore this part also, right? If the physical address not given, still we are able to answer this question. Yes, I hope this is clear. Let's try another question now. Consider 4-way set associative, cache size 64 KB, block size 32 bytes given. CPU generate the 32-bit address. If the k-bit comparator has a latency of k by 10 nanosecond, then its latency of this organization is dash asking now. So now, if you remember or not, time for it in case of which mapping? 4-way. Okay. K-way set association. Okay. In case of set association, we need multiplexer. Time for multiplexer required. Plus, we need comparators also need. Plus, we need OR gate also required now. OR gate. So, this time of multiplexer delay, time of comparator delay, time of OR gate now. So, time of multiplexer plus time of comparator. Comparator means you said k-bit comparator has a latency K by 10 nanosecond is given now. Plus time for OR gate. Now time for it. Okay. In the question, multiplexer delay is not given, make it 0. OR gate also not given, 0. Therefore, time for it equal to K by 10 nanosecond. I should get it now. We should get K. What is K? What is K? K bit comparator nothing but K is nothing but tag bits only. We have to find out the tag bits. So how to find the tag bits? Under this case, physical address is divided into 3 parts, right? One is the tag bits, set offset and word offset, right? Okay. First get the number of blocks in cache. So number of blocks in cache memory. Cache memory. What is the cache memory size here? 4-way set of cache size 64 kilobytes, block size 32 bytes given now. So 64 KB divided by 32 bytes given, right? 32 bytes, right? So this value is what? 2K, isn't it? 2K. So similarly, get the number of sets. So number of sets, capital S equal to 2K blocks divided by, what is the way? 4-way set association is given now, 4. So this value is what? 512, isn't it? 512. We can write 2 power of 9. Now set offset bits will be log of this value means 9 bits required. Set offset bits are 9 bits, if I am not wrong, isn't it? Now set offset bits we got. Word offset bits depends on block size. Depends on the block size. What is the block size? Block size is 32 bit given now. 32 bytes given now. So log of 32 base 2 is 5 bits required now. Now physical address equal to tag plus set offset plus word offset, right? Physical address 32 bits. Tag bits only we need to find out. Set offset bits are 9. Word offset bits are 5, isn't it? So now tag bits will be, what are the tag bits now? So 9 plus 5, 14. So 14 nothing but 6. So 18 bits is a tag. Yes or no? 18 bits are the tag. So now tag latency, time for it. Sorry. Here only. Let me write here only. Okay. Time for it equal to. So K is what? 18 by 10 nanosecond. So 1.8 nanoseconds will come now. So 1.8 nanoseconds answer for this question now. Yes, all of you. I hope this is clear. So look at another question now. If the cache memory is designed a direct mapped cache, the length of the tag bits field is 10 bits assumption now. If the cache is now designed for 8-way set associated cache, then the length of the tag bits dash. Now direct mapped cache is converted into 8-way set association. Now what is the change in the tag bits asking now? Let me take the physical address is there now. Other information not required. We know how it is divided. The physical address divided into, under direct mapping I am taking tag bits, block offset, block number and word offset is there, right? Understand now. Here also physical address. So I am using 8-way set association, right? Let me use first a 2-way only, simplex mechanism, 2-way set association will try. So here is what? Here again tag will be there, set offset will be there, word offset will be there, isn't it? Set offset, word offset will be there. Am I right or not? Now this the physical address, whatever address will not change, some fields will change. So there is no change in this one, right? Word offset will not change, right? So there is a change in block number to word set and tag bits will change. So when I convert this direct map cache to set association, these two fields will change, word offset will not change. Okay. So just observe properly. This gives a number of blocks in cache. This gives what? Number of sets in cache. Sets means what? Number of blocks only we divide, right? Number of blocks only will divide. Example I am taking now. Here blocks are suppose 32 are their assumption now. How many bits required for this? 5 bits required, isn't it? Number of blocks in a cache, assuming number of blocks in cache memory is 32 are their assumption now. 5 bits required. If I use two-way set association, what we do? Number of sets, 32 by 2 will divide it. 32 means what? 16 will come. When 16 means what? We are 4 bit will come, isn't it? Yes or no? When you're changing block to set, 1 bit reduced. If set were reduced means this will get increased or not. If the year is 10, as per this example, it will become 11. 1 bit has increased. What is this 1 bit? This 2 we divided, right? We can make it 2. What you can say log of 2 value. What is the log of 2 value? 1. 1 bit get increased tag. Assume it. Suppose example, I'll use it 4-way set association if I use it. Assumption now. So 32 by 4 I have to divide. When I do 32 by 4, what happens now? 8 will come now. 8 means what? 3 bit happen now here. So it will get increased or not. So now you are dividing 2, right? So log of 2 value is how much? 2. 2 bit is increased. So now with this relation I can make it. I'm making. Let me use this one now. Direct mapped. I'll use it direct mapped. Mapped. So I'll use it suppose first 2-way. 2-way. I'll use it. Let me use 4-way. 4-way. 8-way. Okay, 8-way. Let me use 16-way. Like this P-way is there. P-way use there. Assumption now. I'm comparing. So that generalization I can do it. In a direct map to tag bits, like let me take tag bits. Here tag bits are 10 is given now. Here tag bits will happen. How many? 11 happen. Example we've seen it. Because 2 log of 2 value we have to add it. Here tag bits will happen now. Log of 2 is what? Log of 4. Log of 4 2 bits. It will becomes 12. Log of 8 is how much? 3. So here becomes what? Tag bits here becomes what? 13. Here becomes what? Here becomes what? 14. Here becomes what? Simply what you do it no. Tag plus log of P you should add it. That's it. The existing tag plus this one. How we added? So tag plus 4. Here is what? Tag plus 3. Here what we done? Tag plus 2. Here is what? Tag plus 1 we added, right? What is this? 10 only. 10 bits. This is 10 bits. This is 10 bits only. It is 10 bits. It is 10 bits, right? It is also 10 bits. Whatever number is there now. Simply log P. What is the P? P-way set association. Therefore, my answer is going to be, what is the answer now? So 10 means what? Log of 8 is 3. So answer should be 13 bit. 13 bit is the right answer. Yes, everyone. I hope this is clear. Let's move to another question. Okay. Regarding these two cache mapping techniques, namely full associative cache and direct mapped cache, choose the correct statement. MSQ question. So all of you I'm recommending strongly, when you are studying direct address mapping, like address mapping schemes, study well, revise well. It means properly you study, because MSQ questions highly possible in this area. And sometimes statements are going to be confusing also. Sometimes statements are confusing. You have to be carefully, you have to handle it. Now see, direct mapped cache do not need a cache block replacement policy, whereas full associative caches do. 100% right this one. Direct address mapping itself is a replacement algorithm, because k modulo n I am using. K modulo n position whatever block number will be, that block only you have to place it. It is itself acting like a replacement policy. That is true. In full associative cache, the full address is stored along the data block. In full associative cache, the full address is stored along the data block. Yes, data block, the physical address will be there. That is true. In direct mapped cache, organized according to the index and the tag apart from the memory address stored in the alongside data block. direct address mapping, my physical address is what? A tag and index is there. Index is nothing but block number only. Block number only. This also true. Direct mapping cache may produce more misses if the program refer to memory word that occupies single tag value. Single tag value, same tag value, memory giving references going to the same tag value, nothing, you are in the same block only. If we are mapping to same block, if the block is present, number of misses will not be more. Produces more. No, it won't produces more. Therefore, option A, B, C, 3 are correct. So 3 A, B, C is correct for this question. So I hope this is clear. Let's move to another question. So which of the following statement is or true for the reducing the number of cache misses that occurs certain group of programs? I want to reduce the number of misses. What can be done? Again, the given statement was what are the statements are true? If compulsory misses are most common, then designer should consider increase the cache line size to take the better advantage of the locality. Cache line size. Line size means what? Cache line size, block size. If compulsory means first time coming, correct or not? If line size increasing, number of lines are less, isn't it? Suppose example, I'm taking as a program. Suppose one program I'm taking. The program has, let's take the size is 1000 bytes, 1000 words are there assumption now. I choose a block size is 100 words assumption now. 1000 words by 100 is 10 blocks are referring now. The 10 unique block has to come from main memory to cache. When the block is coming first time to cache, that becomes a compulsory miss. Now what is the point? I want to reduce the number of compulsory misses. Suppose example, I made a program as 1000, when I take a block size 100, 10 blocks comes. This 10 blocks first time when they are coming to cache, 10 miss compulsory happens. These are 10 compulsory misses happens. This statement saying that to reduce this compulsory misses, increase the line size, block size, increase it. If I, instead of 100, 200 if I increase, so number of compulsory blocks will be 5 only now, isn't it? So compulsory misses will reduce, isn't it? Is correct. Capacity misses are most common. The designer should consider the increase of total cache size. Capacity means what? Cache memory capacity. So cache memory size is less, you will keep less number of blocks only, right? You cannot keep it, right? If you increase the cache size, more blocks you can keep it. If more blocks you can keep it, this capacitive misses will be less. Correct on this also correct. If conflict misses are most common, the designer should increase the cache associativity in order to provide the more flexibility when the collisions occur. The biggest limitation of direct address mapping is the conflict misses, isn't it? Because what happens when there is a empty block, even though block might be removed it. To reduce this conflict problem, we use a full associative, isn't it? Full associative means what? You can place anywhere. But full associative is the more costliest one because hardware configuration required highly. Therefore, we moved moderate performance mechanism, set associative. When set size increased, more flexibility, less conflict problems. When I increase set size, conflict problems are less. Therefore, this statement is also true. So I can take the option D is the right answer. To reduce the conflict problems, whether you go full associative or go set association. Full associative is the finest algorithm I can tell, but it's expensive. So we can use it set associative. In practice, most of the processors having the set associative. Maybe a 4 or 8 or 16 set associative methods are used in the practice. Yes. I hope this is clear. Let's move on to some more questions now. The main memory address divided into 3 fields. Main memory address that we call physical address divided into 3 fields. So the least significant W like this, can identify a unique word or byte within a block of main memory. So this is nothing but word observer, correct only. Main memory has 2 power s blocks. Main memory has 2 power s blocks to represent s blocks. To represent these blocks, we need S bits. Yes, correct. S bits required. The cache logic interpret this S bits into S bits as a tag of R minus S. Now here is a tag. So these bits are R minus S used. Sorry, S minus R used it. And the line field of R bits are here. Line field, block number, block offset number. R bits are used. This one now. Number of lines in the cache will be dash. So tell me now. So block, this is a block only, no? So this is a block offset, nothing but number of blocks in cache only, directly, no? Straightforward question now. So therefore 2 power of R lines will be there now. 2 power of R lines. 2 power of R is the right answer for this question. 2 power of R is the right answer for this question. I hope everyone it is clear. Let's move on to another one. Now see. Consider this is related to like cache updating methods you might have studied. Cache updating methods you might have studied. Write through, write back protocol now. Consider write through cache memory is 10 times faster than main memory. 10 times faster than main memory. The main memory access time is 800 nanosecond given. When there is a miss in the cache memory and a 8-word block is transferred from main memory to cache memory. So write miss. Write allocate policy used. What is the meaning of write allocate policy? When there is a write miss in cache memory, we go to main memory, we write it, we will bring extra words. It ratio for read and write operations are 70 and 90% respectively given. System generates 70% read or request. What is the throughput of the system in kilowatts? So now understand throughput. If I want to know throughput, I am writing. So throughput equal to 1 by T average, isn't it? T average, this expression now. How to get this average? So T average access equal to, now here read request, write requests are there, isn't it? Read request and write requests are there now. So now I should take it percentage of read operations, read into 1 read average time plus percentage of write operations into 1 write operation time. I have to take it by using write through protocol. What is the percentage of read operation? They said system generates 70% of read requests. 70% of operations are read only. So I should get 1 read average access time plus 30% will be the write into 1 T average write. I have to take it. Okay. Now first I have to get this value, see clearly, right? So given data, let me take given data. What we need? Cache memory which is 10 times faster than main memory. Main memory access time 800 nanosecond given now. I am writing now. Main memory access time 800 nanoseconds given. Okay, 800 nanoseconds given now. So time for cache is 10 times faster means what? Time will reduce. So 80 nanoseconds the cache will get it. So another information, when there is a miss, when miss in cache, so bring 8 words from main memory to cache memory, right? So 1 word time, if you want to know, 1 word time is, you understand? So for this entire main memory, 800 given now. So now 800 nanoseconds by 8 words. So 8 get cancelled. You can 100 nanosecond per word will happen now. Because I said main memory access time is given now. So when miss occur, we have to bring this one right. Okay. 1 word access time is 100 nanosecond. We can understand. What other information now? It ratio for read and write operations are 70, 90%. So now I'm writing read it ratio HR is 70%. So H suffix are read it ratio. Read it ratio for read and write. Write is 90%. So write it ratio is what? 90% is given. So first of all, I should get this one, right? I should get this one now. I'm writing now. T average read. By using write through protocol, write through updation method also you can see. How to read? First I'll read from cache. If miss occur, I'll bring from main memory. Right. So now I'm writing it ratio into TC. If miss occur means 1 minus R and TC plus main memory, time for memory, right? So he said one word is used. When there is a miss in the cache, miss can be read, miss, write miss it can be, please understand now. 8-word block has to transfer from main memory to cache memory. Okay. Now read it ratio how much given? 70% given now. 70% into 80 nanosecond cache plus 30% into TC is what? This is just a minute. 80 nanoseconds, right? So 80 nanoseconds. Now see, main memory access time is what? When there is a miss, will bring 8 word. 8 word we bringing nothing but 800 nanoseconds only simply. So this value 0, 0 cancel, 56 nanoseconds if I am not wrong. So 0.7 into this one, right? Yes. This value is what? 880 nanoseconds. So overall this value you can calculate. So 320 nanoseconds we got. So T average read. Okay. One more time for updating a memory under write through protocol. So write through updation you should know. So generally will take maximum of TC comma TM will take it, isn't it? So updating. One word you want to update. So now write through protocol for simultaneous updation, right? Write through protocol when you study something modified the processor, we have to update in cache and main memory simultaneously. One word. To one word updating 100. So this is what 80 correct. Sorry. This is 80 nanoseconds comma 100 nanoseconds. So 100 is a maximum only, right? Maximum of this you have to take this I know. So come to the point here. So we have to take this T average write operation now. So now if there is a it, write it is there, we have to update time. We have to update, right? Plus if miss occur, okay, we have to go to update in main memory, plus you have to bring one block, 8-word block have to bring. 8-word block have to bring. This is no, there is a miss in cache, we have to bring 8-word, right? So 8-word block has to come. Time for a block, understand? So 90% into updation time is what? 100 nanoseconds only. T update. We know you might have studied write through protocol, write back protocol. Plus 10% into updated. First you have to update in main memory, bring this one. So 800 nanosecond. So 0, 0 cancel, 90 nanosecond plus 0.1 into 900 nanoseconds cancel. So 180 nanoseconds will get it, right? Okay. Now T average access time equal to this expression 70% into, so 70% into 320 nanoseconds plus, so 30% into 180 nanoseconds, right? So this value will be simplified 0.7 into 320. So 224 plus 0.3 into 180. Sorry. 54. $278 nanoseconds we got. Now throughput equal to, so throughput equal to 1 by T average access time. What is one average? 278 nanoseconds, right? 278 nanoseconds. This I can rewrite 1000 by 278 into 10 power of 6 words per second. I can take it. Thousand by 278. Check it. Nanoseconds only, right? Yes, ma. Just confirm me. Is the values are correct? $320 is correct. 100 is correct. Right operation T update here. Right it ratio. What are the right it ratio is? 90% into 100. 10% 100 plus 800. 900. 90. 90. 0 cancel. Sorry, some calculation mistake. This is 100 only, right? Sorry, 100 nanoseconds, right? 0 cancel. 90 only. 90. 180. 278, right? 1 by 2,000 by this value. So 3.59 I am taking, 2 decimal. So mega words per second I can take it. This is a throughput of the system, memory system, you can say. Throughput of the memory system. I hope this is clear, everyone. Let's look into another question. So write through policy again is used for given a cache. Okay. Cache take 12 nanoseconds to access the tag field within a set and 8 nanoseconds to access the index field of cache set. Memory access time is 500 nanoseconds. 80% memory references are read and read. 20% are write. Iteration for read access, write access given 90 and 80%. What is average access time will be? Same, this same only, but little values are different. So take this given values now. Write through policy only used for given cache. But it did not. What is the difference between previous and this question? Here no read, no write allocate policy used. One is no read and no write allocate policy used. Allocate policy used. What is no read, no write here? When there is a missing cache memory or either read or write miss occur, we no need to bring any data from main memory. That's meaning. Specify, it not specified anything. If specify, you take it. Otherwise, don't take. Okay. So given data take. What is the given data? Cache takes 10 nanoseconds to access a tag field within a set and 80 nanoseconds required to access the index field of the cache set. Simply cache access time I can write it. So TC value is 90 nanoseconds. Together. Correct. 90 nanoseconds. 10 plus 8. Now main memory access time is 500 nanoseconds. Main memory access time is about 500 nanoseconds, right? 80% memory references are read and 20% write. Average access time only. Read it ratio 90%, write it ratio 80%. Let me write it. So read is what? 90%. Write is 80%. If I am not wrong. Correct. This is given data. Now we have to calculate T average. So T average is nothing but, now 80% memory reference are read. So 80% into 1 average read access plus 20% is write into T average write by using write through protocol only, right? Let's get this one now. T average read. First I'll read in cache. So 90%, okay, in cache, right? Cache access time. Right. Similarly, no? Like this only. Before we did, no? Average read. Where is average read? Here on a TC. So TC value. What is TC? TC is 90 nanoseconds. So miss rate is what? 10%. So 90 nanoseconds plus what, 500 nanoseconds, right? Missed will come. Extra we are not bringing, say one word only will come, right? So this value is what, 0, 0 cancel, 18 nanoseconds, right? So 0.1 into 590, 59. Am I right? Correct? So this is what, 77 only? So T average, right? So T average, when there is a right miss occur, if we are not bringing the data, this is simply nothing but T updation time only. So T updation time nothing but maximum of TC comma TM only, right? TC, this is nothing but 500 nanoseconds only directly now. So now T average access time equal to this is 80%, 80% into this value only. So cross check, these values are 0.9 into 90. Okay, not 18, no, sorry. This value is 81. Plus 0.1 into 590 only, right? So this value is 140. So 140 nanoseconds plus 20% into 500 nanoseconds only, right? 0.8 into 140. 112 nanoseconds plus this will be 212 nanoseconds. Option is there, 212, yes. Option is the right answer. Option is the right answer for this question. Next question. So which of the following is or true? So which of the following is or true? Asking question now. In a write-back protocol, cache locations in write-back protocol, cache location, memory location updated simultaneously. So this write-back. So write-back case only main memory get updated, not both. This is incorrect. In a write-through protocol, cache location, memory locations are main memory locations are updated simultaneously. This is true. Modified bits are used by write-back protocol. Modified bits are used by write-back protocol. This is true. Whether this data is modified or not, we can use it. Dirty bits are used by write-through protocol. Dirty bit is not used in write-through. Because that write-through cases simultaneously data get updated, right? So it does not require to maintain any dirty bit. So this way we can understand the questions more. Look at some more. Assume that full associative write-through cache is there. Initially cache is empty. Below is a sequence of memory access given. Different addresses belong to different block numbers here. He asking number of misses using no write allocate policy. This is very important now. No write allocate policy. What does meaning no write? Suppose example, when write miss occur, eventually we should go to memory, we should bring extra. He is saying that no write means if write miss occur in cache, don't bring anything. Just go to main memory, update and come back. Don't bring anything now. If you are not bringing that block, so it is not present in a cache. So I hope this is clear. Example I am taking now. First option, first operation, write memory location 100 is given. First reference goes to memory location 100. So now cache is empty. I want to write in cache memory location 100. So cache is empty, nothing but this becomes miss only. So this operation miss occur now. When cache miss occur, what should I do? I have to go to main memory. I have to write in this location, isn't it? I written. If write allocate policy is there, I will bring block of words. When you bring block of word, this word also will bring it actually. But use clearly no write allocate policy means we are not bringing anything now. I searched in a cache, it's not available. I went to main memory, updated, just I came. Still my cache is empty only, isn't it? Now next. So next reference goes to write memory location, again 100 only now. So now carefully think this operation will it or miss in cache. So this also will become miss only. Why, sir? Because first one writing 100 location, cache miss occur, I written a main memory, I did not bring. So therefore there is no word in cache memory. So same reference comes again miss only now. Now I'm read miss. No write only said. Read can present now. Read memory said now. I want to read memory location 200 no cache. Cache is empty. This becomes miss. Because distinct address right. You know compulsory miss. No? This comes under compulsory miss. Now write miss. So write miss. You understand? Write miss. So read. When you read it, you will bring to what? Cache or not? You will bring to cache. Read miss occur, I went to memory, I brought. He did not use a read allocate. Only write he talking now. So this can be it here now. Because read miss 200 miss occur, now same writing is available in cache. I brought 200 location word from main memory cache it. So now write miss, sorry, write memory 100. Here already miss occur, this also become miss only now. So this is a distinct location, write only write. This becomes what? Miss. Now you are reading right. When write miss occur will not bring anything. We are reading also, this will also becomes miss only. So now you asking question, number of misses, you count it. 1, 2, 3, 4, 5, 6. Yes, answer 6 is right. Total number of misses will be 6. I hope this question is clear. This question is clear. Next question now. So this question related to what? Main memory. Main memory now. A dynamic RAM refresh cycles 32 times per millisecond. Each refresh requires 100 nanoseconds and memory cycle requires 250 nanoseconds. What is a percentage of memory's total operating time required for refresh operation? He is asking now. What is a percentage of the time spent on refresh operation now? He said 32 times refresh happening for 1 millisecond. 1 millisecond happen, right? 1 millisecond. So each time means what? Total time. What is the total time for this one? Total time if you take this 32, right? 32 each taking what? 100 nanoseconds, right? Now this is total time you spent, right? Upon 1 millisecond only now. Now percentage of the time spent on this refresh will be 32 into 100 nanosecond divided by 1 millisecond only. That's it. Out of this time, how much time I spent it now? What is the percentage of time memory total operating required refresh operation now? So this 32 into 100 nanoseconds. 1 millisecond equal 10 power 6 nanoseconds into 100 I can do it. Anyway, fractions he asked it. This we have to simplify it. This gives, so 2 zeros cancel. 4 zeros will be there, right? 2 0 is 0.32 only now. Yes, 0.32 is the answer, right? So like memory based, main memory based questions also were asked 1 or 2 times in the gate. So that you need to observe clearly now. So I hope these questions are clear. Okay. So some observation we can make it related to this, what you can say, memory hierarchy, cache memory consideration now. Average access time of if the system are connected parallel, T1 H1, 1 minus H1 T2, the 2-level system parallel. If it is level by level, this one, 3-level system, level by level. Main memory size we can measure like 2 power of n into m, number of words multiplied by word size, you can say it. So number of words, n is the number of bits required to address the memory, where word length or location size, you can say. So direct mapped cache, physical address divided into tag bits, block offset, word offset, that I written before also. This observation. Where block offset nothing but number of bits required to address the blocks and cache memory. Word offset gives the based on the block size only. So this we know. In full associative, physical address just a tag bits, word offset only will be there. In set associative cache, physical address tag and set offset, word offset, where set offset nothing but log of number of sets. In a cache write through protocol, cache and main memory both are updated simultaneously. In a cache write back updation, no, main memory only updated when a concerned block chosen for replacement. These are the important points which you can observe related to cache memory. Okay. So now in this session I have covered introduction part plus from like a floating point, then memory organization, mainly cache, main memory, memory hierarchy based. So next session I will be taking on tomorrow same time 6 o'clock, in which I will be discussing instruction format, addressing mode, instruction pipeline, very important topic, and DMA control, secondary memory question related questions also I'll discuss it. So I hope you understand this session. I hope it is going to utilize, useful for you. Those who are watching later also go through this session, and one more session also you can go on this COA. Similarly, other subjects also I'm going to plan it. So join our Telegram group so we can get the important updates, and like this class PDF, other things also you'll be able to access it. Okay. So as I told you, IMS offering the online program for 26-27. So it has the good number of features, like as a teaching part is available, live classes plus recording form will be there, around 800 hours will be there. So we are offering every subject is each subject topic like synopsis, theoretical the books are given to you, as well as problem exercise book questions, which covers more than 4,000 questions of all the subjects. And every subject you take in every topic level 1, level 2, level 3 questions are specified it. The main important feature you understand, last 3 previous year questions the book is given to, it has detailed solutions. Okay. And more than 130 test series will get, like subject level, topic level, multi-subject, full length. Okay. And the 12 personalized mentorship session, this is the main unique feature of the IMS, you can tell. Okay. So these are the main features you can get it. So now as I told you also, like IMS we are offering all India mock test series. We already started. It is on the pipeline. Some of the tests, almost 8 tests are on live. Okay. So remaining tests are going to be live in the as per the dates here now. Total 12 test series for the computer science, other branches given. For a data science, we are offering the 6 full length test series. It is what you can say, the same pattern of the gate level, recent gate paper level. The questions are framed it. I hope this session got useful to all of you. Thank you so much for watching this video, and try to subscribe this channel. Therefore, you'll be getting upcoming topics also from computer science especially. So I'll be planning operating system in future, like this December only. Also I'm planning computer networks and even possible compiler design, theory of computation also I'm going to plan it. Even other subject also will plan it eventually. Thank you all. Thank you so much everyone.